So let's take a look. Just as a refresher, our differences between galvanic versus electrolytic cells. Remember, galvanic or voltaic cells are the spontaneous one. Their cell potentials are going to be positive for their reactions as written. Electrolytic are the non-spontaneous reactions. So these would be ones that come out with a negative E cell when we actually look at our balanced electrochemical equation. So again, I think we saw this image before, but just kind of the big differences between our two cell types for our galvanic or our voltaic cell. They're the spontaneous one, so our system is going to do work on the surroundings. For electrolytic, our surroundings, our power supply, our battery, our plug-in is going to do work on our system. In terms of our free energy, energy is being released from our spontaneous reaction. It is going to be absorbed by our non-spontaneous. Our big differences within the cells themselves. For our voltaic cell, we've got two different half reactions and then connections via this external wire. For our electrolytic, it's one pot, but we're still seeing oxidation at the anode, reduction at the cathode for both. The only big difference beyond that, one pot versus two pots, is our kind of denotation on the anode or electrodes themselves. Before we said our anode is going to be the negative, our anode now becomes positive, and that's because we're using an external source to actually remove or force the electrons away from there. And our cathode becomes the negative electrode. That's where our electrons are being forced again from the power supply. In terms of our reactions, we've seen these before. The only big difference is our sign connotation on our free energy and our cell potential, our E cell. Just as a refresher, a non-spontaneous reaction can be brought about using electrical energy to have our chemical change occur. There's a couple different reasons we would want to do this. One is if we had some form of electroplating. This is how we get all of our kind of plated materials, is through this process of electrolytic reactions. It also is how we actually get reactive elements back out of their ionic solution compound. So for example, here we've got tin 2 chloride. By running electricity through here, we actually have the tin played out at the cathode. Our cathode is our reduction gaining of electrons. Oh yeah, so our tin 2 plus, Sn2 plus, is turning back into our regular old tin. And then at the anode, oxidation, loss of electrons, our negative chloride ions turn back into chlorine when they lose their electrons and become neutral once again. So this is how we go about getting a lot of our different reactive elements out for us to then use in chemistry class to react to see chemical changes occur. It's going to be a direct current, so just a little bit here on our electrolysis reactions. Electrolysis uses direct current. Our cathode, again, is going to be our negative. This is where our electrons are coming into the reaction. Anode is positive. Here our electrons are moving away, leaving it more positive. Anions flow to the anode. Cations flow to the cathode. Our electrons are going to be lost by the anions. That's where oxidation is going to occur. Our electrons are taken from the cations. That's where a reduction occurs. Sometimes you got to overvolt it. You got to get more juice going through there than what your reaction tells you should in order to initiate that reaction. It just is sometimes necessary to kind of get those electrons flowing and get our half reactions to occur. But the good news is to figure out that voltage, it's the same process that we did for our spontaneous reactions. We take our two half reactions, figure out which one's the anode, which one's the cathode. We combine the two, we add them together to then get a cell potential. It's just now, instead of it being a positive value as written, it will be a negative value. And so that negative value will tell us how much we need to get it to go. So for example, our sodium ions and chloride ions can be separated via a redox reaction. To do this, we would have our kind of sodium chlorine in solution, sodium salt water. Our sodium ions would flow to the cathode to plate out sodium. Our chlorine would go to the anode to come off as chlorine gas. Again, they're reversed. Our battery or our voltage or our power supply actually moves the electrons physically for us. If you're going to figure out what's going to happen, we got to start by figuring out what changes are taking place. So here we're at the anode, our positive anode. We're going to have two chloride ions actually turn into chlorine gas and lose 2 electrons. Our sodium is going to gain them. We would then figure out our cell potential for both. Here we've got our two values. We get those from our standard cell potential. If we had to flip, so for example, for our oxidation reaction, we'd have to flip it. So the sign flips as well. We then add the two values together, just like we've been doing for our other half reactions. And so here's the amount of energy we have to put in, and that's really what that negative sign tells us. We have to put in at least 4.07 volts in order for this reaction to go. This tells us the voltage we would have to apply to the half reaction for our plating to occur. So anything above 4.07 volts would get these two to then start to plate out. Cool. It's kind of brief introduction, kind of the differences between our galvanic and electrolytic cells, and how we actually determine what voltage is necessary in order to get that plating to occur.